Вот, ну, третий. Еще раз прыгнем. Начни сразу, практически сначала. Раз, два, три.
Good afternoon. My name is Asılbekova. I am teacher from Nazarbayev Intellectual School of Physics and Math stream from Astana. Right now you have seen some small clip about our students and the work we did in the laboratory. What do you think? What will be the topic of our lesson today? Actually, yes. And today we are going to talk about physical quantities and measurement. From very beginning of our life, we start to study everything which is around us. And one of the way of study it is making measurements or measuring. What does it mean to measure? If you ask somebody to tell the size, for example, of high building, or for example, battery, or how wide is your classroom, or what size do you wear, everybody can answer. Maybe not exactly, but we are able to do. And all things is due to the measurement. So, what does mean to measure? Measure, it means to compare any physical quantity with someone which is used as a standard. So when we do the measurement, we have to use some devices. Very famous English scientist Lord Kelvin has taught, when you can measure what are you speaking about and express it number, you know something about it. But when you cannot express it is numbers, your knowledge is of meager and unsatisfactory kind. So we should take these words in account and try to do our best. Our integrated program about developing physics suggests us the next learning objectives. So we have to know difference or distinct systematic errors, including 0, 1, and random errors. Also, we have to know and understand the difference or distinct precision and accuracy. And the last important things which you always meet during our practical work, it's to calculate uncertainty. It can be done by numerical way or graphical. When we ask today question, what do you think we do? And I mentioned some words, it's maybe sounds strange, not used in our ordinary life, but it's special language we have to use during our subject actions, and we call it language of measurement. So everybody knows to measure, you have to take object of known length, for example, a ruler, and use object with unknown length, and can compare them and can tell exactly how long or how much this object is. Now let's look at this
the current and voltage. The connection between electrical voltage and resulting current is measured with various test resistors.
The material that we need is 2 resistors, circuit plate. Also we have to use voltage supply and of course this ingenious
machine
called spark.
Yes, it is instrument for measuring physical quantities. Yes, and in normal experiment we use ammeter and voltmeter, but instead of them we use this spark, this instrument, and the voltage current sensor. Yes, and to do this experiment, we have a scheme which we use to connect all these test resistors. Yes, and we set up the experiments as shown in the picture.
So then we start measuring and complete the chart below. That is
For
given
each
us.
resistance, for resistance 1, and afterwards we output this resistor and put the resistor 2, and we measure its measurements,
Yes, and connect them.
connect them,
Parallel.
connect in series. Yes, and afterwards we complete all these charts and do a
Diagram.
diagram. Yes, the graph, and make a conclusion of this experiment.
Okay, you have seen right now that the student have explained how they did going to do this practical, and one of the main things to understand what they are planning to do, and it's because it takes time. The first responsibility of the student is to manage time. So we should decide themselves how long we can do this measurement, and in order to make decision about when the measurement should be repeated, it should be appropriate. You have noticed all preparation for practical work should be done in advance, and all observations, data, reasoning should be planned in a way which were easy to follow, easy can be performed. Typically we prepare some sheets when we give some scheme with written every about name of the work, goals set, or sometimes we can set themselves, and some tables for recording. Even though we have done some measurements, we are not be sure that our measurements is absolutely perfect, and therefore there is key terms which define the quality of our measurements. They are validity, accuracy, precision, measurement uncertainties. And what problem can the students meet when we do observation and after we decided to record the observation or data of measurement? There are special requests or rules to complete or to record all the data. One of the common way is filling the tables. So look at the tables, please. The first we should pay attention on it is headings. Each heading should contain quantity of measurement and the units in what the quantity have been measured. So all readings made directly from measuring instrument should be given to the appropriate number of decimal places. Look here, we have always written 2 decimal places for I, for current, for example, and here we have also written for 2 decimal places. The next, if you're going to write readings from some instrument, we should also remember about scaling, about size of division, and that's why, for example, the data for reading taken from a ruler should be given to the nearest millimeter, because millimeter was the size of division. Another thing related to the quantities calculated from the raw data, we should show if the correct number of significant figures. Here, for example, according to the raw significant figures, we have 3 significant figures in all data for voltage except the last one. This last one contains all 4 and therefore should be rounded. In many cases, rounded simplify our calculation, but in same times we can make us our results worthy, because sometimes we can hide our information which can be very important. So, but let's consider the rules which we should follow when we do some calculations. Rule for calculating signal figures. When we add a subtract, we have to round our answer till the least number of decimal places. Least number of the decimal places. Look here, we have the decimal, the smaller the least number is 1, that's why our answer should be rounded till the first digit after the comma. If you look at this example, you see the 4 decimal places, and the answer should be also keep same number of decimal places. Another things happen when we multiply or divide. In this case, we should follow the number of significant figures, last significant figures. So, in our first example, we have significant figure number of 5 for the last second member. That's why rounded happens also till the 5 digits, not figures. And with our sample, we see also only we have 3, because the tailed 0 is not significant. That's why we can round till the 3 digits, or 3 significant figures in our answer should be. What do you think? Are you good in significant figure determination? It's topic new in our physics maybe, and but it plays important role, and therefore that's why you should learn how to determine the numbers. And there are a lot of the electron resources, internet resources for the students. So you can find with one when you can only insert the data and get all information you need. Even we try to do all our measurements, we also sometimes cannot get the proper results, and maybe sometimes our measurements are not good and strange, and therefore because we can avoid some errors which accompany our measurements. In physics we can find 2 types of error. What do you think? What is error? Error is not mistake. You should again remember these things. Error means something which is not good, perfect done, or do not correspond to some data. Therefore, we divided the errors in 2 large groups. First one is systematic error. The reason of systematic error is in instrument or technical use in our measurement. If you would like to calculate, for example, free fall, I have to use stopwatch, and I have to use a ruler, and maybe I did not, and with all of them have some limited things, and all the time when I do this experiment, I'll have same results. We cannot avoid them. So, but there are ways to improve it. It means if you take instead of the large calibrate or my greatly calibrated ruler, you see calibrated in inch or centimeters. If you take another ruler which is have smaller size of division, I can improve my results. So often we do not follow the rules stream of normal vision, for example. Our eye should be directly against the pointer, for example. But if you look from above place or below with this pointer, we can disturb, our results can be unusual, or can some differences will be different. So depends on the devices we use, we can always have some systematic errors. But we try to do it each time to avoid them. Look here. What do you think, what kind of error is it? We decided to measure the current with help of electronic digital device, and we know the current should be not over than 55 millimeters. But our ammeter shows readings 80, 58, 59, 59, 57 and 58 milliamperes. In this case, if you calculate the mean and find its value, in our case it will be 58.2 milliamperes. It does not eliminate systematic error because it's over than 55 milliamperes. This case is considered as a systematic error. Another cases or another type of errors is which we call random. So some situation can happen while we do measurement. Maybe temperature outside change or outside when we do some experiments, or does not matter in the room or outside. Maybe some voltage fluctuation happens, or we have suddenly jerk and then maybe look at not. So we do not expect with the things happened, and that's why we influence our result. Such kind of errors we call as random errors. And they are really important to try to avoid them because they affect precision of our results in measurements. So sometimes we can try to avoid them, sometimes it's not possible. It's very important to know. For example, again, reading of voltmeter, we know according to the passport of this device is not over than 12 volts. But voltmeter always reads 12.5, 12.0, 13.5, 11.0, 12.5. If you now calculate mean, it means average value, we will get 20.3. It's very close to our actual readings or value. That's why we can tell that calculator mean reduce our error. It is type of the thing random error. Okay. Even depends on our practical skills, or sometimes due to the occasional, we not started from the fixed zero position. And in this case, we have some deflection from the original, and we have got so-called zero error, one of the common case. But we have to differ. For example, micrometer screw gauge, what is shown on the picture, it has two scales, and both scales should coincide in order to start, measure, and get appropriate value. So you see the difference between zero here and zero of the supplementary scale. In this case, this zero is called positive, and this will be inverse negative, and we should take it away from our results to subtract. It can improve our measurement. Next part of our lesson will be devoted to the concept of accuracy and precision. I'd like to ask you, what do you think? What is accurate measurement? What is precise measurement? Many times people confuse, mostly people in every ordinary life can tell you, give you answer, oh, it's the same things. Doesn't matter what accurate or precision. But it's true. But it's very different picture, situation you have in physics. Let's define the terms accurate measurements. So, suppose you have a lot of measurements, take a lot of measurements, and if you see your measurements or reading are very close or agree to some acceptable value, we can tell that we have done our measurement very accurate. Look, if you know exactly value for free-fall acceleration, according to the table, it's in average mean is 9.80 in some meters squared. But We have got experimental result 9.903 meter squared. And this result will be greatly accurate when the, for example, result can be expressed as a 10.6. So acceptable value is 9.8 plus details, and we will consider what result is accurate or not. Now please maybe mention what do you mean about when we talk about accepted value. Some quantities we have measured very strictly, and we have very high precision, and they are known. We call maybe the table data quantities like free fall acceleration, universal gravity, constant gravitation constant, charge of electron, mass of electron, gas universal constant. And all data we know and use in our calculation we call as acceptable value. And it tells us define how accurate measurement we have got. Now, different things happen when we talk about accuracy. Accuracy. We again taking a lot of measurements, and we see we have got some set of the data, and we see they each close to each other. We have 5 trials, 6 trials, and it means in this case we can see we have do very precise measurement because they close over. But set of these measurements is defined by number of decimal place, because they define let us to tell about precision. Now let's consider this next activity. One measurement has taken 3 times, and we know the correct measurement was 60.8. If you have free data of 3 students, and we should decide which one measurement is accurate, precise, both precise and accurate, or neither, nor precise nor accurate, neither precise nor accurate. So if you look carefully, we can notice that our data should be given 8.1 millimeter, and if you look and through this data, we can see the option B has the data which is close to the correct measurements, so we can call it very accurate. But you see that all measurements are of the same order, about same day value, and we can say it as accurate and as well as precise. So we can choose, for example, answer both. Okay. It's easy if you look on this example. You see, with a load of 100 grams has been weighted, and you see one balance scale showed 100.2 digital 0 after comma, but second one show only 98.98. So this is inaccurate measurement because it do not coincide with the proper value. Very often, or maybe to simplify our understanding, because it's not so easy, we use with a picture when we use targets, and we have some see. If you see the all data, all our shoots will come to the center, we can go, we have accurate because we are correct, we get exactly to the center of this target. But if you see all our trials get some position and all of them are close to each other, with like we do some consistent actions, we call it precise. In the case of precise, you can tell yourself when all data should be in the circle, and the distribution should be same only in the circle. And this kind of measurement we call both accurate and precise, because precise measurement can be accurate. What should you remember when you're talking about degree? What do you think? You know, we have taught many devices which we're going to use in our experiment, in our measurement, will define our result, final result. That's why. And the accuracy and precision depend on each other, maybe stand against. So it depends on the device and unit. If you take a millimeter scale or took the ruler tape, we get different results. So, but there is general rule. The degree of accuracy all the time is a half of unit from each side of the unit measurement. So, our ruler is scaled in maybe 1 millimeter, 1 centimeter. So, the value from all sides, it means plus minus half of the 0.5 to the left and 0.5 to the right, tells about degree of accuracy. And all other instruments measure any value between 7.5 and 6.5, and we consider is a measure of 7. Please remember. I just would like to mention the information given on this slide. It told about real fact happened recently when the people start to explore or use Hubble telescope. Because manufacturers provide to give him accurate devices, but we would not something happens, and the radius of curvature was precise to 0. micrometers, but was inaccurate in 2 millimeters, and it led to the bad picture, and in this case the company also not even lost the money, but lost time, and they lost their reputation. So be very careful while you do some measurement, and even be responsible for production you make. The measurement never can be perfect. I'm just repeating these things, and our practical, we have to train ourselves, we have to use think about equipment we are going to do, we have to plan about, we should plan our actions, and but all the time our measurements have some uncertainty. What does mean uncertainty? Uncertainty tells about degree of accuracy or precision when we measure. So we call it uncertainty. So it tells in how much it differs from the standard or expected value. It means some deviation from some data. If you usually we have two types of devices. More old-fashioned is an analog scale, but very useful and durable, and we have digital scaled devices. So please look and remember, for analog scale devices, the uncertainty will be the half of the last division of the scale. So if we have 1 millimeter scale rule, our uncertainty will be half of this one, and half of the size of division. But for digital scale, we have to look at the last significant figure which displaced. So it's we can plus minus add to our final results, and in this case our result will be between 8.93 and 8.94 plus minus 1. For analog device we have 6.55 and 6.65. How do we record uncertainties? Typically we record is a way measurement. The measured value is equal to measurement got in experimental and some uncertainty. This type of uncertainty we call absolute one. So absolute uncertainty is denoted with half of the symbol delta, which means change, and the quantity symbol we have used. In general, we can use x. So delta x means change. If you measure some quantities, the plus minus number unit in measurement is denoted like delta x. It will be absolute uncertainties. If you, for example, measure length, it will be 2.34 and plus 2 minus millimeter. In this case, we have 1.6 plus minus 0.3 millimeters. With an absolute uncertainty, let us to know the maximum value and minimum value of measurement. And absolute uncertainty has unit. Look here, if you measure length, it will be in centimeter scale, centimeter. If you use millimeter, we can also express in millimeter. So, and do not forget about units. Absolute also uncertainty deals with precision of the instrument. This is an example which leads maybe to consider in detail how can you find absolute measure uncertainties. If you're going to measure ball bearing with help of the micrometer, you know, we will measure and we have got some set of the numbers. So, next step we have find average reading or mean. You see, just add all data divided by number of the measurement trials and have got 1.21 millimeter. So, our results will be lay in the range between maximum value and minimum value. Maximum value will be 1.25 we see here, and the minimum is 1.18. So the range will be 0.07 millimeters. It was maintained that the error or uncertainty always is equal to the half of the range. So our uncertainty will be half of the range. In our case will be 0.035 millimeters. And because our data we have measured in precision which was expressed by two digital places, so our diameter's final result should be written in the two digital places, and you see measurements and its absolute measure uncertainty. So in average the balls or ball bearing has a size 1.17 till 1.25 if you add or we subtract. Another thing we call about percentage uncertainty. For percentage uncertainty, we should mention it can be expressed or typically used two ways: fractional and percentage. So it means ratio of absolute uncertainty to the measured and expressed either in numbers or just in percentage. Look at this example. Length is 234 plus minus 2 millimeter. So to find percentage uncertainties, we have to divide it 2 millimeters over 234 and multiply by 10. In this case, we have got 8.5. We write this way in the bracket, and do not forget about millimeters. But you look at here. Our percentage uncertainty has no units. Let's continue consider our previous example, and you see we can calculate fractional uncertainties. It will be 0.3, and we can percentage uncertainties, which is expressed in the percent. So 0.03 or the 0.0 percentage. It is relative uncertainties. I'm just going to show, I would like to go to show on this slide examples of recoding. For absolute error, again, I remind you about units. For relative, no units. This problem can be solved, just we look and understand. If you, for example, meet this problem, rectangular object has length and width given by with measured with some uncertainties. Can you tell me what will be length uncertainty in the length? Okay, absolute will be 0.2. For width 0.5. So we can find relative uncertainty in the length and width. How can we do it? Remember, if measurements are combined to form some quantities, like in our cases, for example, area, or just another way, we should remember should take in account and know the rules. There are two main rules which related to addition and subtracting. When we add or subtract, we should add absolute uncertainties. Look here, absolute uncertainties only. Doesn't matter will be plus or minus. Two quantities are plus or minus. So if you divide or multiply, we add relative uncertainties. In this case, we should find relative uncertainties and only when later. Let's consider these examples. So, for example, side of the fence measured with the tape and have some data. It also known given the uncertainty of each measurement is 0.07 centimeters. We have to find perimeter including its uncertainty. So what we should do? We just add some measurements and got this data. Then we have to find the uncertainties because it's a fence. We have remember to calculate and take it the root of them, and we find 0.14 centimeters. So final result will be 662.0 plus minus 0.1. And pay attention, we round it till the one significant digit, like it was given. Another example. Multiplication, rectangular. In this case, we have given two sides have been measured, uncertainties also are given. Our task is calculate the area. You see the rule, we should multiply two quantities or measurement and one use this formula. If we're done with one, we multiply two quantities and then we find relative uncertainties and then also find square of them and then take root of them, square root of them, and got this result. So if you see why we did, we can leave only with answer, and in this case we decided to round it till integer numbers. Think why we did it. One more example of multiplication, it means in this case when we measure free fall acceleration with help of the height, we can find, for example, or we know the free fall acceleration, we decided to know from what position it was thrown, and we can use again the rule about multiplication on constant, because C is constant, in our case G is constant. So this rule helps you to know how to solve this problem, and you see another examples you can see, you make a trend in order to be very sure you can understand these things, you can do these things. And let's look at a very simple slide chart. You see some voltmeters, DC voltmeter, analog one, and the readings is shown is 10.11.6 we suppose. So absolute uncertainty 0, we can tell 0.2 because it's the half of size of division. You see it's calibrated in twos, we can divide it by smaller one data, and when we have recorded our data, we see the fractional uncertainty divided by absolute uncertainty over measurement quantity, and percentage is also the same thing but calculated in percent. This is differences between them. Look me carefully one more time. So, you see in our ECP program we have some learning objective recommended which check our understanding and knowledge, but for what? We have to be able to apply this knowledge. So we are going to assess applications ability. And you see, according to our criteria-based assessment policy, the students achieved with learning objective if he or she fulfills 5 out of 6 criteria. It means it will be equal to 83%. So, I have prepared some task for the students, and I have defined 5 criteria. First criterion is related to the absolute uncertainty and the ability to turn from one uncertainty to another. Second one, in inverse, when relative uncertainty should be expressed in terms of absolute uncertainty. And the 4 other examples are given to the determining appropriate uncertainty in the case of addition, subtraction, multiplication, and division. Look at this task. You see, first one, 2 options, second one, 2 versions, third one, 2 versions. The same things we have to for the rest of the tasks. So, while you go in to check if I were a teacher, I can just give for one options because they are similar to the students, and they may work by individually, or we can work in pair, discuss, maybe interact. But for formative assessment, we should give this assessment by versions and check. If student do everything wrong, you can tell that he has achieved the goal. One of the quiz can be also suggested is that I'm going to show the samples. For example, it's maybe multiple choice questions. So, in this case, it said which is not acceptable. If you remember what is the uncertainty, what is absolute uncertainty, what do you think? How much is absolute uncertainty in this case? Yes, 0.5 centimeter. So, to give answer, we should find maximal value and we should find minimal value. Maximum value should be 4.05 and minimal 3.94. If you look now at the data, we can see with C options, which is equal to 3.94 is less than minimal one, so it's not acceptable. To give answer, we should remember the definitions, we should be trained, we should know how to calculate, and easy to find. In this case, it's very easy to find proper answer. We have no time today to mention about graphical presentation of certainty. It takes time, but I'm just showed maybe for further study the notions. We call it bar arrow, which bar arrow also can express the uncertainty of the measurement and influence of the graphical presentation of our results. So, what can I say in conclusion? All people now know the measurement plays some significant role, take position, which very important. So we can say measurement provides structure, remove chaos, reduce waste, ensure open and fair markets, support precision when required, and save lives, money and time. I'll be very appreciated if you give me some reflection on these lessons. So I suggest you to answer me this way. I'm in the first. I know many things, or I know something from these lessons, and write maybe 3 or 3 words, just maybe some phrases. So second, I'd like that you tell me if I like something from my lessons. Okay. And the third thing, I suggest you to think and tell me, if I were a teacher which should conduct this lesson, what I'll change? These notes will be very useful for me, and will help me to just improve the lessons and maybe conduct this topic more better way. I'd like to thank you for collaboration. All materials will be available on the Moodle site moodle.kz, and main resources used for preparation to these lessons are the literature or maybe resources which have been prescribed by our integrated program. It's textbook Sang and Jones, and from Cambridge International University Press. Second, when we use teaching AP and to physics practical skills, because all things I have told today related to the practical skills development. So, and we also the course plan for 11th grade improved this summer will be also taken for preparation, have been true for preparation, and to assess our knowledge, we have used criteria-based assessment recommendation for the teachers. Thank you. See you.